You ever wonder how scientists can actually trust each other's super complex computer models? I mean, how do they build on someone else's work, or even argue against it if they can't see how it was made? Well, today, we're going to unpack a really crucial tool that makes all of that possible. We're going to crack open what's often called the black box of modern science. Right, and this really gets to the heart of the problem. A lot of these powerful scientific models, they kind of feel like these mysterious black boxes, you know? They spit out these amazing, fascinating results, but what's going on inside, the recipe, so to speak, can be so complicated or just badly explained that it's next to impossible for other scientists to recreate it, to compare it, or, let's be honest, to even trust it.
And look, this isn't just a minor inconvenience. It's a major roadblock to scientific progress. This black box issue is a really big deal, especially when we're talking about some of the most powerful tools out there, things like agent-based models. Okay, so what in the world is an agent-based model, or ABM? Well, think of it this way. Instead of using big, sweeping, top-down equations to describe a system, an ABM flips that script. It simulates everything from the bottom up. You create these little individual agents that could be virtual people, animals, even companies. You give them a few simple rules to follow, and then you just let them go and interact. And here's the magic part. You get to see what incredibly complex, system-wide patterns pop up just from those simple individual actions.
All right, so if that's the problem, how do we actually crack open that black box? Turns out there's a really elegant solution. It's called the ODD protocol, and it basically gives everyone a common language, a shared blueprint for describing these super complex models.
What ODD really is, it's a standard template. It helps scientists write down everything about their models in a consistent way. And the name itself, ODD, tells you the whole structure. O for overview, D for design concepts, and another D for details. It's a pretty simple idea, right? But it has absolutely huge implications for making science more transparent.
And this quote really nails the ultimate goal, to create a lingua franca, a universal language for these simulations. Just think about it. With ODD, a scientist studying tiger populations over here and a totally different scientist modeling how people use land over there can finally look at each other's work and actually understand the basic structure and logic. It's about building bridges between completely different fields.
And the benefits of having this common language, they are absolutely huge. For one, it makes replication possible. And that's the bedrock of all science, right? It lets people reuse parts of models, which saves a ton of time. It makes it way easier to compare different models. And of course, it builds that all-important trust and transparency. It's really about weaving the entire scientific community closer together.
Okay, so we get why it's so important. But how does the ODD protocol actually work? What does this blueprint for clarity really look like when you break it down?
It's all broken down into three logical parts. First up, you have the overview. This just sets the stage, what's the model for, and who are the key players. Then you get to the design concepts. This is the really cool part, the secret sauce of the model. How do the agents behave, learn, and interact with each other? And finally, you have the details. This is the real nitty-gritty stuff, like the initial setup, the input data, and the specific equations that make the whole thing run.
So, let's make this real. Here's an example of what that overview part looks like, taken from an actual model of a tiger population. You can see it clearly lays out the entities, in this case, female and male tigers, and their state variables, stuff like their age or the territory they control. There's no guesswork here. Right from the start, you know exactly what's in the model.
Now, in that design concept section, this is where it gets really interesting. OOD makes scientists get really clear about abstract ideas, like emergence. It forces them to ask, are the results we're seeing truly emergent? You know, unexpected patterns that just bubble up from all the little interactions? Or are they imposed? Basically, predictable results that the scientist hard-coded into the rules. Making that distinction is absolutely critical if you want to understand what a model is really telling you. But here's the thing. Having a perfectly described model isn't the finish line. It's the starting line. It's the solid foundation you need. Because once you have a model that everyone can understand, that they can trust, then you can move on to the really critical next step, actually analyzing what it produces. And this brings us to, like, the million-dollar question. One of these models can produce just mountains of data. You've got dozens of different knobs and dials, parameters, that you can tweak. So how on earth do you figure out which of those things are the ones that actually drive the results? Well, the answer is a super powerful technique called sensitivity analysis. It's basically a formal way to poke and prod the model to see which of those parameters have the biggest bang for their buck, which ones have the most impact on the final outcome.
It's all about separating the signal from the noise. And this chart here, this shows a sensitivity analysis in action. So for this particular model, which is looking at agent migration, you can see that the number of agents is by far the most important factor. It explains about half of the final result. The tolerance level, yeah, it matters a bit. But the initial random seed, it barely makes a dent. This is the kind of clarity we're talking about. It lets you truly understand what makes the model tick.
Okay, so let's zoom out for a second and tie all this together. I know a documentation protocol sounds super technical and maybe a little boring, but why does it matter so much for the big picture of how science gets done?
Well, this number pretty much says it all. Over 4,000. That's the combined number of times the original OSDD protocol papers have been cited by other scientists. That's not just some niche tool that a few people are using. That is a massive signal that scientists across the board see the value in this. They recognize how badly a standard like this was needed.
So, at the end of the day, the ODD protocol is so much more than just a fill-in-the-blanks template. It's really a pillar that supports the most important values in science. Being open, being rigorous, it's all about choosing transparency over black boxes and clarity over confusion. To put it simply, it just makes science work better.
And that really leaves us with one final thought. We're using these incredibly complex models to try and understand some of the biggest, toughest challenges we face. We're talking climate change, economic meltdowns, you name it. So in a world that's this complex, isn't having a common language, a clear way to describe and debate the tools we use to understand it all, isn't that more important now than ever before?